video is about dimension of physical quantity. The dimension of any physical quantity expresses dependency on the base quantity as the products of symbol or their power representing the base quantity. Another word for base quantity are those fundamental physical quantity that we have talked about, which is length, mass, and time. So for example, the area would have the dimension of length square, and speed, like mile per hour, would have the dimension of length per time. When we talk a dimensionless quantity, you can think of it as say L to the 0 power, mass to the 0 power, and time to the 0 power. So a quantity to the 0 power is just 1, 1, 1. So a dimensionless quantity is a number. Okay. We use the brackets around the symbol to represent the dimension. So for example, R for radius, so we put the brackets around R that's equal to L is length. Brackets around A is equal to length square, and brackets around V is L to the Q. So bracket around, say S for speed, is length over time. Okay. So these are the symbols that we use for length, mass, and time. What is dimensional consistency? Okay, dimensional consistency states that equation must obey the following rule to make things consistent. Okay, every term in the expression must have the same dimension. So the way to remember is you say you cannot add apple and orange. Okay, the expression on each side of inequality, okay, say A and B, must have the same dimension. Okay, so the way to remember is you cannot equate apple and orange. The argument of any standard mathematical function, such as trigonometric function like sine, cosine, tangent, logarithmic or exponential function must be dimensionless. Remember, it's just a number. What's this dimensional consistency do for you? So it helps you to check your work, and it helps you to remember equation better. So for example, sometimes you say, is the area of the circle pi square or 2 pi r? So remember, area is have to have length square, right? So this is where the r, the dimension of r here is length. So this square here will be length square. So this must be the correct one. Okay, not this one. So it helps you to remember which equation is the correct one. Let's do a few examples to check dimensional consistency. So consider the following physical quantity. S must be for distance. Okay. It's L, length. V, this must be abbreviation of velocity. This must be distance. And A is for acceleration. So velocity is length over time. Acceleration is length over t to the square power. And dimension of time is t. Our job is to determine whether each of the following equation is dimensionally consistent. So let's start with A. We have S equal, so this is the equation. So checking dimensional consistency mean we're going to check this dimension of S. Is it equal to the dimension of VT plus 0.5 dimension of this term? Okay, so that's the question. Okay, is this dimensionally consistent? Okay, so let's do each of the term on the right. So VT is dimension of V multiplied by dimension of T. Dimension of V is L over T, and dimension of T is T, so that's L. So dimension of this term is L. Then next, 0.5 a to the square. Dimension of 0.5, dimension of a, dimension of t to the square. Dimension of a number is called dimensionless, is nothing. Okay, and dimension of a is length over t to the square. And then dimension of t is t squared. So now we cancel. And that's also give us L. So let's put in out the number that we have. So on the right hand side we have L. On this one we have L and L. Okay. So each of the term have the same dimension. So this good check. And then the right hand side also have the same dimension. So yes, it is dimensionally consistent. Okay, let's do B. So this equation, say S equal VT to the square plus 0.5 a to the square. Oh, actually, that's just AT. Now, if you notice that this 2, it just swap for this 2. Right? So which equation is correct? Okay. So this is how dimensional consistency would help you to check. So we need to determine dimension of S. Is that equal to dimension of VT squared plus 0.5 AT, dimension of that. So let's do VT squared, dimension of V, multiplied by dimension of T squared. Dimension of V is length over T. Dimension is T and then square. So you end up with LT. Okay. While dimension of 0.5 AT is dimension of 0.5, dimension of A, dimension of T. So that's 1 is length over T to the square, and then we multiply by T. So this gives us actually length over time. So if I was to put this in, this first term give me LT, and the second term give me L over T. So they are not the same. So you cannot add apple and orange. And then over here they have length, and you cannot equate apple and orange either. Okay, so this add is no good, this equal sign is no good. So this is not dimensionally consistent.